Alrighty. Good morning, everybody, and Happy New Year. Hello, and welcome to the wolfSSL live webinar on how to get started with wolfSSL with wolfSSL engineer Chris Conlin. My name is Kaushal Subkota, and I will be moderating this webinar. All attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the question live, as we do host a Q&A session following this presentation. This webinar will also be recorded and made available on our YouTube channel shortly after the presentation. And I invite everyone to follow us on Twitter at wolfSSL, as well as all of our other socials. And please feel free to email us at facts@wolfssl.com if you have any additional questions. And now I'd like to give a brief company overview before we move on to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source, dual licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2022, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team have developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the version 5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSC support, and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand it over to Chris for the presentation.
Great, thanks, Kajal. Hi, everyone. My name is Chris Conlin. I'm an engineering manager here at wolfSSL. Thanks for joining us today, and welcome to 2022. So today, this is our agenda. We're going to walk through, starting with an overview of SSL and TLS 1.3. Then we'll go into looking at the wolfSSL library, an overview of the package structure, building a library, some of the applications that we ship to make testing and benchmarking easier for you, look at basic library usage, and then share a couple of debugging tips that we think are helpful. Hopefully I'll have time to kind of do a live demo of our wolfCrypt test and benchmark applications. And then, like Kajal mentioned, we'll have some time for Q&A at the end. So starting out with the SSL and TLS protocol, the protocol is not new in of itself. It started in 1995 with the first public version being SSL 2.0. SSL itself went through 2 revisions, 2.0 and 3.0, before it changed names to TLS, or Transport Layer Security. TLS has gone through 4 revisions, the most current of those being 1.3, which was finalized in 2018. Kind of paralleling TLS development has been DTLS, which stands for Datagram TLS. And this is a version of TLS designed to be used over unreliable protocols like UDP, oftentimes used in things like VoIP applications. So if we look at TLS 1.3, this is just a timeline of the development. It's been out and finalized for a couple of years now. It was finalized in August of 2018 with RFC 8446. And with TLS 1.3, there were some substantial protocol changes, including algorithm changes, removal of insecure features. Most of the handshake messages are different, and there's more of them that are encrypted. There's a new 0 round trip mode where application data can be sent in the first with the first client hello message. Redesigned key derivation functions, and also changes to how session resumption are done. So what are the advantages to you as a user? The biggest first advantage is faster performance. So TLS 1.3 requires one complete round trip for the SSL TLS handshake, whereas TLS 1.2 and before required two complete round trips. So this one less round trip means that network latency has less of an impact on the time required to establish a connection. And optionally, you can take advantage of the zero RTT mode if you're set up to do that in a secure manner by sending application data earlier. It's also more secure. So the protocol designers removed a lot of the legacy and insecure algorithms. Some of those you can see listed here on this slide. And so it makes it harder or nearly impossible for users to use these now since they've been removed from the protocol specification. And then also in the security category, having more encrypted handshake messages makes it harder for an attacker to see what's going on in the handshake. TLS 1.3 can also be more flexible for some use cases. There's a new key update mechanism, which allows the protocol at a connection to reestablish without shutting down the session and doing a new session. And so the key update message can be sent anytime after the handshake has been completed. TLS 1.3 allows post-handshake authentication, so you can do your certificate authentication anytime after the handshake, in addition to doing it during the handshake like previously done. And then the removal of some of the old library features and algorithms can help you reduce your library footprint size. That's beneficial to users who are on constrained devices trying to fit into a small amount of memory. So if you want to learn more about TLS 1.3, we do have some great information on our website and much more detail. We have one web page that's a good starting point for you if you go to wolfSSL.com/TLS13. So if we look at where is SSL and TLS located in your stack, this is a simplified diagram of the OSI model. And so it's layered between the transport and application layers. Here you can see this would be in TLS 1.2 and before. The blue boxes here are the SSL and TLS subprotocols. Green boxes here are examples of application protocols that can either sit on top of the transport layer or on top of SSL and TLS for a secure variant. TLS provides three main goals to the end user: authentication, confidentiality, and integrity. And then when we're looking at the OSI model here, typically we're sitting on top of TCP/IP, but really, since we're above the transport layer, you can be running any transport protocol underneath that you have available to you. This is a simplified diagram of the TLS handshake, which would be TLS 1.2 and previous. And so here you can see there's a number of round trips. Kind of the goals here are to exchange certificates, authenticate the peer, and then establish the set of algorithms that are going to be used and the keying material for the connection. TLS uses what's called a cipher suite to represent the algorithms used in that session. And so here you can see the format of a cipher suite in TLS 1.2 and previous protocols. So it starts with the protocol, a key exchange algorithm, a bulk encryption algorithm, an optional mode, and then lastly followed by a message authentication function. And so if you have configured TLS before, you've probably seen something that looks like this. Here's some examples of the TLS 1.2 cipher suites. Now with TLS 1.3, the cipher suite string representation changed. And so it removed the key exchange and signature algorithm from the cipher suite itself. And so here you can see now it's just the protocol followed by your encryption algorithm and mode, and then lastly, the message authentication function. And with TLS 1.3, now since those, the key exchange and signature algorithms have been removed, we're only left with 5 defined cipher suites that the RFC has given us. So next up, let's look into the wolfSSL library. A little overview first of all, and some of this is a slight duplicate from Kajal's overview, but we'll go through this quickly. So wolfSSL supports up to TLS 1.3 and DTLS 1.2. Footprint size is typically 20 to 100 kilobytes, depending on your build configuration and platform. Runtime memory is 1 to 36 kilobytes per session. And this footprint size is up to 20 times smaller than OpenSSL, so it's going to fit into an embedded or IoT type device much more easily. We've ported wolfSSL to almost all of the OSs and RTOSs that we've encountered to date. So you can see our current list here on the bottom of this slide. That's your standard platforms, as well as a number of RTOS environments, all the way down to just a bare metal environment. Some other features of wolfSSL, we have an OpenSSL compatibility layer. This is a mapping of the most commonly used OpenSSL functions down to wolfSSL APIs internally. That can be helpful if you're trying to migrate or port over from something that had been using OpenSSL in the past. We've plugged into a number of the most popular web servers, including Apache, Nginx, Lydie, and Mongoose. We have support for quite a few hardware cryptography platforms now. So if you have hardware crypto available in your silicon, we can offload and use that crypto instead of using the wolfCrypt software crypto. And so this typically provides us anywhere from 6 to 10 times performance increase. wolfSSL is NSA Suite B compatible, and we also do have certified and validated versions available for FIPS 140-2 and soon to be 140-3, DO178C for avionics, and also just NIST CAVP algorithm validations at the crypto only level. One thing we like to do is port wolfSSL into open source projects. And so in 2021, we were really focused on expanding our list of open source projects. This is some of the kind of the recent and more popular ones that we've done. We do have more than this that wolfSSL can plug into. But if you're using these, keep in mind that you can use wolfSSL underneath now. One place to look is our open source projects repository, or OSP, which I've linked here on the bottom of this slide. That's where you'll find a number of patches for these projects that will allow you to plug in wolfSSL, wolfCrypt. So wolfCrypt sits underneath wolfSSL. This is our crypto library. Here you can see the algorithms supported by wolfCrypt. This is all of our standard algorithms, in addition to some more progressive ones like SHA-20 and Poly 1305 and Curve and Ed 25519. You can use wolfCrypt standalone. You can also use per algorithm in a standalone manner if needed. And one thing we've been working on in this last year is to fill out some of our support for post-quantum algorithm support. And so we've leveraged the liboqs library as a starting point to now provide us with Falcon signature scheme support, Kyber, Entrue, and Saber key exchange groups, and then the hybrid groups on the right are combining some of the traditional ECC curves along with post-quantum algorithms. And so if you're more interested in this, we do have a webinar focused just on post-quantum crypto, which is very interesting to listen to. So to get wolfSSL, you can download it from our website or from GitHub. We do put our stable releases on the website, and we tag them on GitHub. So whichever is easiest for you to use. Once you download wolfSSL, the next helpful thing is we have a lot of things in our package now. So I'm going to go over in the next couple slides kind of a walkthrough of what you'll find in the wolfSSL package once you download and unzip it. And so here we have the directory structure of a fresh downloaded and unzipped wolfSSL package. I'm going to start at the top and kind of walk down through some of the commonly used areas here. So the first thing you'll run into is an IDE directory. This is going to include a lot of our compiler project files for popular compilers like the Arduino IDE, Eclipse, GCC ARM, Raleigh Crossworks, Renaissance, eSquared Studio, etc. And so if you just want to be able to open up a wolfSSL project in your IDE or compiler and hit build, this is likely the area that you would like to look into. Next down, we ran to a certs directory. This includes our example certificates and keys. And so we use these for testing. They can also be helpful for just getting up and started and prototyping quickly. Obviously, you shouldn't use these in production, but for testing and initial prototyping, it makes it easy to get started. The configure script is what you'll want to use if you're configuring and building wolfSSL in a Linux or Unix environment that has autoconf. And we'll go through some building instructions in a few slides here. You'll see a couple directories called crypt and cyazzle. This is a backwards compatibility layer for our old naming scheme. wolfSSL used to be called cyazzle before we changed the name. The examples directory has an example client server, echo client, and echo server. These can be a good API usage reference if you're looking at how to use an API in a client or server. It can also be a good place to test with. If you're working on a client, you can test against the server or vice versa. We do have more examples that are smaller and more concise available on GitHub in the wolfSSL-examples repository that I have linked here. There's a gencertbuff.pl. This is a Perl script that we use to generate C arrays from certificate and key files. So if you're on a platform that doesn't have a file system available, this is something you could use to convert a certificate into just a C array for use on that platform. Next, we'll skim all the way down to the wolfCrypt directory. This is our source directory for crypto layer files. The wolfSSL subdirectory is our header or include directory. And so directly under wolfSSL, you'll find our SSL and TLS headers. The wolfCrypt headers are under wolfSSL/wolfCrypt. And our OpenSSL compatibility headers are under wolfSSL/OpenSSL. At the bottom, you'll find a number of Visual Studio solution files. If you're on Windows, you can import or open those up in Visual Studio and have an easy way to build wolfSSL along with some of our example projects. And then the last directory here is called wrapper. This is our C# wrapper for wolfSSL. One thing to note, we do have other language wrappers, but because of their size, we choose to bundle them separately instead of putting them inside of the wolfSSL package itself. So now that we've downloaded wolfSSL, we've looked at the package, the next thing to do is how do we build wolfSSL? And so if we're on a Unix Linux type platform, you can easily use the configure script. If you move into the wolfSSL directory, run /configure with the options that you would like to configure, enable, disable, etc. You can then run make. That builds the library. And when you're ready to install the library, you can run make install or sudo make install. Configure does have a help option, --help, which will list out all the available enable or disable options that we currently support. There are a number of them now, probably upwards of several hundred for all the different algorithms, different modes, different hardware support, etc. This is just an example of how you would configure enabling ECC and enabling DTLS. If you need to define a define and pass that through configure, you can do that using the cflags variable. So here we're defining an example _define. You can run make check. That will compile the library and also run our built-in tests. So this will run our API unit tests, a test suite that we have, as well as a couple other things. And then sudo make install or make install will install the library. The default installation location is user local. So you'll end up with headers in user local include wolfSSL, and the library will be installed into user local lib. Artifact names is just lib wolfSSL. If it's a shared library, .so or .dylib on Mac, and a static library is .a on Linux or Unix. So compiling wolfSSL on Windows, most of our Windows users are using Visual Studio. They can use those solution files located in the root of our wolfSSL directory. And we do have projects for a lot of our examples, test suite, and a couple other things. If you are on Windows and want to use Visual Studio, we do have more in-depth documentation on the website as well. We do support Windows users who would like to use Cygwin to compile. And so the required packages will be GCC, automake, autoconf, libtoolmake, and unzip. And then after that, you'd simply just follow the autoconf instructions that we covered a couple slides back. There's an install file in the root of the directory. This is helpful to point you in the right direction of how you compile for some other platforms. So for example, if you're using IAR eWarm or Kyle, MDK-ARM, and you want to know where to get started, that's a good place to look. So the kind of the next category of users are people that want to just pull wolfSSL and wolfCrypt source files directly into an IDE project and compile that together with their own source code. And so you can do that pretty easily. You just need to know what files to pull in. And so the SSL and TLS source files are under the /source directory. The header files for the TLS layer are under wolfSSL. The crypto layer source files are under wolfCrypt source, and the crypto header files are under wolfSSL/wolfCrypt. So looking at portability, portability's really been one of our primary design goals of wolfSSL since the beginning. We've tried to abstract out pretty much any OS, platform-specific, transport layer-specific dependencies, things like I/O, memory, endianness, threading, file system time, and such. And so you have an easily usable way to override these things. You can see our existing port layers in the wolfSSL wolfCrypt /settings.h file. Typically, we'll have one defined per platform. So for example, if you're on FreeRTOS, you'll see a FreeRTOS define that you can enable. Likewise, if you're using LWIP, we have a wolfSSL LWIP define. And one thing that we know is a common thing for users to have a need to do is to define and customize the wolfSSL library with some custom preprocessor defines. Not everyone is using the configure script, and not all of our defines are exposed through the configure script. And so what we recommend doing is if you define wolfSSL _user _settings while building wolfSSL, wolfSSL will automatically try to include a header called user settings.h. And so you would write your own user settings.h and put all of your defines in there to configure the library. So then that makes it easy to migrate from wolfSSL to wolfSSL releases, meaning you only have to really maintain that one file. For examples of things that you can put in there, we do have a good example under the IDE Raleigh Crossworks ARM directory. And we also have some reference kind of pre-made user settings.h files under the examples/configs directory. Okay, so next up is a couple of our applications that we ship with wolfSSL. We have a wolfCrypt test application and a wolfCrypt benchmark application. And so the test application, this is essentially a small application that runs crypto test vectors through all the enabled algorithms in wolfSSL by default. And it verifies the crypto is working correctly on your platform. And so we recommend this is the first place you start when getting wolfSSL running in a new environment. If the crypto is not working correctly, you're going to run into probably a lot of other problems at a higher level at the TLS layer. And so the wolfCrypt test is located in one file under wolfCrypt/test. There's a file called test.c. It is compiled by default when you just run make if you're using autoconf. And the executable is called test wolfCrypt. If you run that from the root wolfCrypt/test/test wolfCrypt, you'll see output that looks similar to what you see on the right hand of this slide, essentially just going through all the algorithms telling you if the test passed or test failed. The second application that we ship is a wolfCrypt benchmark application. So again, this is in one file called benchmark.c under the wolfCrypt/benchmark directory. And what this does is benchmark all of the enabled algorithms in wolfCrypt, giving you performance numbers that you can use to either compare between configurations, compare between flat platforms. And sometimes people are, we're also using that to compare against, say, hardware cryptography being switched on or off. If you're interested in just looking at some reference benchmarks of this being run on different platforms, the website linked here is somewhere that we put a lot of those reference benchmarks. So the benchmark app is compiled also by default when running make. The executable is just called benchmark, and you can run it from the root directory by running wolfCrypt/benchmark/benchmark. It benchmarks all algorithms for at least 1 second, giving you the performance of that algorithm. So if we look at the default structure of test.c and benchmark.c, they do kind of assume you're running on a desktop-like system. They include a main function, they use certificate and key files, and they do benchmark all enabled algorithms by default. But they can be customized to make it easier to use on an embedded target. And so there's a bench embedded define, which you can define to reduce resource usage. If you're on a platform that doesn't have a file system, you can use one of these three defines here to switch those over to use certificate and key buffers or C arrays instead of files. A lot of times, if you're on an embedded target, you already have kind of your own main driver function. And so you can define main driver, which will compile out the main function from these applications. That'll then expose a driver function that you can call called wolfCrypt test or benchmark test. If you call those, it'll run all the enabled algorithms by default. You can also run individual algorithm tests or benchmarks by using their dedicated API. So now let's move on to how you use wolfSSL kind of at the most basic level. So the first thing you're going to want to do is make sure your application is compiled using the same preprocessor defines as the wolfSSL library. This is important because if you compile your wolfSSL library with one set of preprocessor defines in your application with a different set, at runtime, you can run into some really weird errors in things like the math library or the ASN library, or just algorithm configurations. And so if you're using autoconf and configure, that will auto-generate an options.h header for you that essentially dumps all of the preprocessor defines that autoconf had used to configure wolfSSL into this header. And so your application can just simply include wolfSSL/options.h, and you're ready to go. So the second header, most likely, if you're using the SSL and TLS layer, will be SSL.h. This is our main SSL and TLS API header. wolfSSL has two main structures, a wolfSSL structure. This represents a session, and a wolfSSL CTX structure. This represents a context. So a context is, you can think of it as a factory for sessions. An application will typically have one context and then multiple wolfSSL structures per session. You'll initialize the wolfSSL library with wolfSSL init. You can optionally enable debugging with wolfSSL debugging on, or turning it off with wolfSSL debugging off. You will need to have compiled the library with debug symbols by enabling debug with enable debug or defining debug _ wolfSSL. You'll then go to create a wolfSSL context. So here we're creating one with wolfSSL CTX new. It accepts a protocol version function that has the protocol version and the side. So here we're using TLS 1.2 on the client side. You can enable or set how peer verification is done by using wolfSSL CTX set verify. Set verify does accept the third argument there is a verify callback. So if verification fails, wolfSSL will call that callback and let you do additional inspection if needed. Then you need to load in your trusted root certificates. So you'll do that using wolfSSL CTX load verify buffer if you're loading it in from a buffer, or wolfSSL CTX load verify locations if you're loading those in from files. So after that, your application would go off. It would create a socket, it would connect the socket. Then you'd come back and create a wolfSSL session for that connection using wolfSSL new. If you're using TCP/IP with socket descriptors, you'd pass that to wolfSSL using wolfSSL set FD. Then you can do the TLS handshake either on the client side by calling wolfSSL connect, or on the server side by calling wolfSSL accept. When that function finishes successfully and returns SSL success, the handshake has been done and you're ready to send and receive data securely. So you can write data using wolfSSL write and read data using wolfSSL read. When you're all finished with that session, you can shut down using wolfSSL shutdown. That sends the close notify alert to the peer and optionally does bidirectional shutdown, receiving the peer's close notify alert. And then when you're all done, you'll free up your resources at the SSL level, at the context level, and at the library level. So for API reference, chapter 17 of the wolfSSL manual covers wolfSSL. We also do have Doxygen available for wolfSSL and wolfCrypt, and you'll find that on our website. The wolfSSL example client, like I mentioned, can be a very good kind of usage example of the wolfSSL API. that's located in examples client, client.c. Now the wolfCrypt API is also available to you. Each algorithm has its own header file typically. So for AES, there's a wolfSSL wolfCrypt AES.h. Each algorithm also typically has its own structure. So here you can see AES has its own structure called AES. For wolfCrypt API details, you'll want to reference chapter 18 of the wolfSSL manual. A couple notes on thread safety. wolfSSL is thread safe by design, meaning multiple threads can enter the library simultaneously. We do this by trying to avoid, using global data, static data, sharing of objects. There are two exceptions to this case, which you do need to be aware of if you're using us in a multi-threaded environment. So the first of these is that your app can share one wolfSSL session across threads, but you must access control that object access. And so, for example, you can't read and write to the same wolfSSL object at the same time from two different threads. That'll end up in undefined behavior. The second exception case is that your application needs to completely initialize the wolfSSL context before starting to make sessions from it. And so you can imagine if you have one thread making the context and you spawn up another thread that makes a session before the context is completely initialized, the session will inherit kind of an incomplete context state. And so what we recommend doing is having a single thread initialize the context, and then you can go off and do your multi-threading from there. So a couple notes on debugging wolfSSL. The debug logging can be very helpful. You can enable it with enable debug, and then after wolfSSL init, calling wolfSSL debugging on. This is what you'll see from the debug log, or similar to what you'll see. You'll see entering and leaving functions, details of the handshake process, details of certificate parsing, and really it lets you easily see kind of the context around an error that happens. And so if you're working with our support team, we'll commonly ask you for a debug log of wolfSSL. The second thing helpful for debugging can be to leverage the example client and server. Like I mentioned, if you're developing a server, you could use our example client as kind of a known working client, and vice versa. Wireshark can be a very helpful tool to use. You can see what's happening inside of your connection. It allows you to drill down and inspect details of the TLS messages. And it can also be very helpful to send us to our support team if you're having problems. A lot of times we'll ask you to send over a Wireshark or a PCAP trace of the failing connection. So now I'm gonna try to do a quick live benchmark for you of our wolfCrypt test and benchmark applications. Let me see if I can switch my share here. Okay, so here we have this is just a wolfSSL directory that I've just downloaded and unzipped. This is our wolfSSL 5.1.1 release. You can see the directory structure looks very similar to what we covered at the beginning of our package structure overview. So from here, we can run configure. That'll go out and detect a bunch of things about the environment that we'll use during compilation. And you'll be able to use configure anywhere you have autocomp, whether that be Unix or Linux, or in my case here, I'm on Mac. When configure finishes, you get a summary of all the features that are enabled and disabled by default. In this build, you'll get some information about the compiler and the C flags that are set. Once configure passes, we can run make. That'll compile the library. It also compiles our examples. It compiles our tests, and also the two applications we're looking at here. So to run the wolfCrypt test, we'll run wolfCrypt /test/test wolfCrypt. This will go through and test all the algorithms that are enabled in the library. Here you can see that all of the algorithms have passed for us. We can then run the wolfCrypt benchmark by running wolfCrypt /benchmark/benchmark. like I mentioned, this will run a benchmark in all of the enabled algorithms for at least 1 second. Here in the first section of algorithms, it gives you throughput in megabytes per second. Also on supported platforms, you'll see cycles per byte. So you can see we walked through some of the encryption algorithms, moving through some of the message digests here with SHA, SHA-2, and SHA-3, moving into HMAX. And then when we get down to public key operations here, you'll notice the metric changes. Instead of megabytes per second, we now have operations per second. So that's the result of the benchmark. You can see it'd be very easy to go back and do a make clean to clean up the library, change some configure options. So we have, for example, AES GCM lets you configure things differently. So you could go back and reconfigure, rerun the benchmark, and then compare the performance and how that changed. You could also go and enable hardware crypto if you're on an embedded device and see the performance difference between software and hardware crypto. So with that, I'm going to open it up for questions and turn it back over to Kajal to manage that process.
Awesome. Yeah, we have a couple of questions here. We have a question here from Marcus, which is, when is DTLS 1.3 expected?
Yeah, so DTLS 1.3 it's definitely been on our roadmap for a while now, ever since the draft has been working, been in progress. We do have it on our roadmap again for this next year. And so we'd like to start looking at it. We just don't have a specific time frame to give you yet. Part of that will also depend on customer demand. The more people that we hear that are looking for it, the faster it'll get implemented.
Awesome. How do you support HTML5 video with or without OTT video mix in the streams?
Gosh, that's a good question. I'm not sure I know the answer to that off the top of my head. Typically when we're getting into the HTTP layer, that's outside of wolfSSL itself, unless that code requires specific APIs or integration points into wolfSSL. But if that is TLS related, our support team would be able to point you in the right direction there.
Awesome. We have another question. What is the performance gain typically when using SHA-384 versus SHA-256 in TLS 1.3 in standard frames like 500 TCP bytes?
Yeah, so the performance difference, is largely going to come down to the difference between SHA-256 and SHA-384. So what I would recommend is, run the wolfCrypt benchmark like we did here and look at the throughput difference between the two. We do have also another benchmark application I didn't show you, but we have in the library there. That's a TLS benchmarking utility. And so you can run a benchmark of a Cypher suite inside of a TLS connection. And so in there, you could run it on the two Cypher suites you're curious about and see the difference there.
Fantastic. This is regarding web server integration. Have you launched this in cybersecurity use cases like healthcare workflows, or any other use cases where compliance is very stringent?
Yeah, so in general, we do have a lot of customers using things like Apache or Nginx with wolfSSL. One kind of reason why you might want to do that is to have a certified or validated version of wolfCrypt underneath. And so, for example, you could use wolfCrypt FIPS underneath wolfSSL in Nginx or Apache. And so that could help you meet some requirements for compliance, depending on what you're trying to achieve in different industries.
Awesome. What is the enable distro option? This person is building for an embedded 32-bit PowerPC environment using a manufacturer provided board support package?
Sure. So embedded distro, so that build option came about when we started working with package maintainers for things like Debian and Ubuntu. And we needed to provide them an kind of our recommended configuration to use in a package for those distributions. And so, for example, Ubuntu or Debian would use enable distro to enable our default set of things that we recommend there. That is going to turn on a lot of things, since in those cases we're kind of assuming you're on a standard desktop type system. And so if you're on an embedded system, I'd probably recommend you not use that, and instead build up your list of enable options based on more of what you need, rather than just kind of the more heavy-handed enable distro, just to save you some footprint space.
Fantastic. Why does wolfSSL expect UTC, time in environment?
So there's a couple places wolfSSL uses time, and so kind of the big consumer is for doing certificate validation. And so this, certificates have a validity period, not before or not after a specific date and time. And so that's when we'll need access to an accurate time source on a platform. We do have customers that don't have that available, and there's a couple options there. In a best case world, you are able to do time verification, but we do have ways that you can disable just the time verification or date verification checks if needed.
Awesome. How do I use the new CTX new function, or how do I use the CTX new function if I want to enable both TLS 1.2 and 1.3?
So there's a couple things you could do. So if you want to support both of those in the same context, we have a kind of a more generic protocol method that you could pass to that called wolfSSL v23 client method or server method. And so what that'll do is when you make a connection, it'll start at TLS 1.3 and downgrade to a kind of a minimum downgrade level that you set. So you could set your minimum downgrade to TLS 1.2, for example, and that would allow you to only support 1.2 and 1.3. The other option is you make two separate contexts, one that supports explicitly 1.2 and one that supports 1.3, and then use one or the other depending on which connection and which area of your application you're in.
Awesome. NTP was mentioned as a port against open source projects or against an open source project. Can you give more information about that?
Yeah, so NTP is just an open source project that commonly is available on systems, and so we plugged into that, essentially replacing the crypto that was there and plugging in wolfCrypt. And so if that's a build combination that you're interested in, we do have a kind of a recipe for that, and probably set of patch files. Off the top of my head, I'm not sure, but I would guess you could contact our support team at support@wolfSSL.com and we could send you the right things.
Awesome. Yeah. This person needs to port a new embedded target with no operating system. The toolchain exists only on Windows. Any advice on how to get that started?
So on Windows only, I guess, you're kind of the two things that we see there most commonly are Visual Studio or, something through like Cygwin. It's, if you're using Cygwin or MinGW or something that gives you the AutoConf system, you can run configure and just set your, -- host equals to your toolchain, and that'll take care of, usually take care of setting the compiler and the linker and things like that. I would probably recommend reaching out to our support team just to get kind of a generic recipe for a bare metal environment. That would be something you'd put into user settings.h that then you could use in that build system just to turn on and off the right things inside of wolfSSL that might depend on OS dependency or something like that.
Yeah, awesome. Is there any plan to support platform security architecture crypto API for wolfSSL or wolfCrypt?
Yeah, so that's something that we have started looking at is the PSA crypto. We don't have anything available per se yet, but it is something that will be coming down the line in some capacity. Again, kind of the direction that we take there will depend on what we're hearing from users. So if you're looking to use that in a specific way or on a certain platform, reach out to us and that can kind of help direct us in our efforts.
There are a few .s files in the wolfCrypt SRC folder, but they don't compile when built for MQX. Are they needed to build the library? And they've given an example. For example, AES_ASM.s.
Yeah, so what those are is those are assembly files. And I believe that specific one is for Intel AES-NI. And so that'll only be applicable if you're running on an Intel chip that supports the AES-NI extensions. So for MQX, we wouldn't expect those to be built, and you can safely exclude those from your project.
Awesome. What is your opinion? Can we use wolfSSL through mutual TLS or TSL use cases in mission critical workflows and cloud, like Red Hat or IBM is pushing?
Yeah, I think when you say mutual TLS, I'm guessing that person is referring to mutual authentication, where each side is authenticated, both the client and server. That can definitely be used in wolfSSL. We support mutual auth or just single-sided auth of the client and or the server. There shouldn't be any problem using it in a Red Hat type environment or an IBM type environment. And we do a lot of testing on wolfSSL to make sure it's secure and we're confident that it can be used in mission critical areas or more sensitive areas as well. If you'd like more info on our testing and some of the assurances we can make there, we do have that information available too. We'd be able to send over.
Awesome. When adding new tested platforms to 3389, who does the CAVP testing? Customer on the proprietary platform or wolfSSL?
Yeah, so 3389, that's our second FIPS 140-2 certificate. And when we do FIPS testing, a customer will send us their exact hardware, and wolfSSL will handle all of the testing in-house, including the CAVP or now ACVP testing as part of that process. And so the customer just ends up with essentially the new OE listed on the certificate as a deliverable.
Fantastic. What is the wolfSSL Linux kernel module and how would it be used?
Yeah, so the wolfSSL, the Linux kernel module is a new packaging method for us, I guess I would say. And so it allows wolfSSL to be used inside of kernel space on Linux. And so we test most of the popular kernel versions right now. And so if you need to use wolfSSL in kernel space or link wolfSSL against something that's in kernel space, that's where you would want to use that.
Fantastic. And does the wolfSSL library allow scatter loading?
I'm not exactly sure what the user means by that, but I believe the answer to that is no, that it's a wolfSSL is compiled as one shared object, and that object is loaded at runtime, either dynamically or linked in statically, optionally as well.
Awesome. That was the last of our questions, I think. Thank you, Chris, so much for a fantastic presentation. And thank you, everybody who, has attended this webinar. As a reminder, this webinar is recorded and will be made available on our YouTube channel shortly after this presentation. If you would like to receive a copy of the slide deck, please email us at facts@wolfSSL.com and we'd be happy to send that over to you. And as always, if you have any more questions or comments, please also email us at facts@wolfSSL.com and we'd be happy to talk to you. Thank you so much. And I hope everyone has a happy new year.